And the organizers for giving me a chance to present my work. So since 1.5 years, I have moved to TIFR. And as you see from the title, I will be talking to you about the detection and characterization of exoplanets, the diverse kind of exoplanets around the diverse kind of stellar hosts. So like we discussed many talks which were around gender equity. I'm not actually spending any time talking about that. But interestingly, I just thought in the morning, like we need special equity corrections to bring certain section of the society at par with those who are underprivileged or so. Some of the star planet correction, some of the star planet systems need extra interventions or extra care in order to bring them to the detectable limits. So I will be talking about few such interesting things where the detections range from varied kind of planets to stars. So actually, the field is not very new to say because people were trying to search for planets since half a century or so. But the interesting bit was there was no successful detection for quite some time. The first planet was discovered around a pulsar in the early 90s. But what really set the field was the discovery of the planet around a solar type star. So this discovery was marked by the detection of 51 Pegasi b. And these two gentlemen, Michel Mayor and Didier Queloz, they happened to win the Nobel Prize for it 5 years back. So this discovery was in 1995. And what set the momentum was the planet discovered was half that of a Jupiter mass, and it was around a solar-like G-type star. So what you see is actually the radial velocity detection curve from the discovery paper. The interesting bit about this thing is, if you just imagine in our solar system, the nearest planet is Mercury, which is 88 days apart. And having to just compare to another planetary system, where you see that the nearest planet is just 4.2 days, it was very puzzling to the astronomers at that time. And these astronomers took a lot of time convincing the community that, look here, there is a planet, and it actually exists. So there were multiple spectrographs which were pointing towards it. And finally, it was established. Many people tried to also confirm this, and they could as well do that. So that was the mind-boggling discovery of that time. I mean, today we have quite a lot of exoplanets discovered. And if you see in this graph, I've plotted, I mean, it's a graph taken from online exoplanet archive, Caltech, which is maintained by Caltech. So you see the cumulative distribution count of planets around the discovery year, and you see nearly an exponential growth. The detections are colored by the varied detection methods, and you can easily notice most of the planets are colored in this purple and green color. So these two detection methods are considered to be the most popular. They are as well my favorite because I work on both of these detection methods, the radial velocity ones, which are colored by green, and the purple ones are colored by the purple ones indicate the transit detection method. The other methods are equally important, but due to some challenges or the other, there hasn't been enough discovered planets in that space. But hoping that it changes soon, because each discovery method looks into some other space, like another orbital period or another mass class of planets, and it's very important to understand the whole picture of exoplanet architecture. So let me talk a little bit about the radial velocity method. So here the star and the planet system actually go around a common center of mass, which means even if you do not see the planet, you detect the slight wobble of the star by looking at it from a spectrograph. So you see the absorption lines of the spectra move towards the left or right, depending on how the star is either coming towards you in the projected orbit or it's moving away from you. So that is what enables us to detect another object around it. The transit method sounds much more simpler, wherein you're just looking at the complete light which is coming from the star. And if you happen to have a planet or another star also, this can be possible, which is going around this star, then you see a decrease in the intensity. The depth will actually tell you what the size of the planet is. And in the earlier example, the mass is what influences the radial velocity. So you can infer the projected mass from the radial velocity method and the radius through this. And also, you can estimate the total duration of the transit the time spent when the curve actually dips down. This gives you a handle on the inclination, the thing which is not very sure in the radial velocity method because the angle is always projected. So that sin I also gets solved. So if for systems you have both the radial velocity and the transit method, that enables you to talk about the density, which is a very important property of the planet because that will tell you if the planet is Jupiter-like, gaseous, or it's Neptune-like, or it's Earth-like, rocky or so, because we really are not at that level to send probes to exoplanets. What we can infer is to the bulk composition and through some atmosphere studies. So for my PhD, I worked at the Physical Research Laboratory. I was not actually working on exoplanets for my PhD, but I was involved in a high-resolution spectrograph, which is called PARAS. Now they have another copy of it on a larger telescope at that time. While I moved for my postdoc at the Thüringer Landessternwarte in Germany, where I spent 6 years before I started at TIFR, there also was another 2-meter class telescope. With a combination of such 1 to 2 meter class telescopes where we had radial velocity spectrographs, not the extremely precision kinds, we were easily able to detect Jupiter-like planets, the 51 Pegasi B kind of planets, around a wide variety of like solar kind of stars. So what interestingly we found was there were many planets. So this is a graph where we have plotted such discovered Jupiter-like or hot Jupiters. So planets which have an orbital period of less than 10 days, they are called as hot Jupiters. They have been plotted across the radius and x-axis, and they are equilibrium temperature. So how do you calculate the equilibrium temperature? Basically, you know what the stellar host temperature is, and based on the orbital separation, you can compute what could be the equilibrium temperature. So if you just plot this graph, you happen to notice that most of these planets, they have a relatively higher equilibrium temperature because they are situated very close to the planets, and in some cases, the host stars are as well hot, but they in general, since they have a larger atmospheric scale height. So this enables them to absorb a lot of radiation, and then they become thermally hot. And this is very interesting because such hot Jupiters are good examples to probe in the atmosphere species. So they're excellent candidates, not only from ground-based observatories, but also from missions like JWST. And JWST has contributed excessively. So why people like us are important to go to the next step? Because in order to apply such techniques to for any exoplanets, you need to have the precise knowledge of the mass. So unless you do not have, if there is an error in the mass calculation, the species that you are going to identify would not be right. So it's of utmost importance that there are precision spectrographs who can determine the radius and masses of such objects. So this was the exercise that we carried out by small telescopes, and we discovered a handful of exoplanets around them. But that was not the end of it. There are planets that can be smaller than Jupiters, and probably spectrographs which are more precise are needed in that case. When I talk about the term precise or more precise, it just means that the ability to detect the smallest of planets. So if, for example, I'll give you a number, if one wants to detect a Jupiter in a sun-like orbit, like placed at 5 AU, you have to have a radial velocity amplitude of 12 meters per second, which means in order to detect such a planet, a spectrograph which has a radial velocity precision of 5 meters per second should be good enough to detect a Jupiter in that orbit. If the Jupiter is put in closer to your star, this amplitude will be like hundreds of meters or in kilometers, which means even a worse spectrograph can detect it. Now imagine detecting an Earth-like planet at the same place where Earth is around Sun. This radial velocity amplitude is just 9 centimeters per second, which means detecting such small planets makes it really very, very tricky. So definitely not normal spectrographs. You need a very ultra high precision spectrograph. Plus, there are other things which just star does, and you need to eliminate all those other things as well. So then we had several projects which were also running on other spectrographs, precision spectrographs like HARPS. Maybe some of you would have heard the name. So we started a program where we looked at solar-like stars and started to look if they have Neptune-like planets because they were very interesting. Now, let me tell you by a fact. So, well, we discovered many. I would just point out one discovery that we put out a paper last year, just the recent one, where we discovered a planet which was Neptune-like. Neptune-like means the density was very much like Neptune's. Neptune has a density of 1.6 grams per cc, and this one had very close to 1.5. But what differed was Neptune is situated at a very further out orbit in our solar system. So it is an icy planet. So the core of the planet is icy, and the atmosphere is roughly 20 to 25% hydrogen and helium. Now, based on the modeling, theoretical modeling that we did, based on the radius and mass estimates that we had of the planet, we discovered that this planet that we found out would only have either 1 or 2% of hydrogen helium envelope. And the core of the planet could either be Earth-like, full of silicates and metals, or it could have a mixture of water and silicates. So there are some things which you really cannot break down. The models has degeneracy because there's only limited information that you retrieve out of it. Maybe when you do more atmosphere measurements, there are certain lines which can tell you about where the planet could have formed, and that can give you insights more about such discoveries. But this was what I wanted to point out, that these Neptunes, which are orbiting relatively closer to their host star, is completely absent in our solar system. But we could only discover this class of planets when we started to look at other solar systems. So this makes it very imperative that if we were not looking at such systems, we would have never known what wide variety zoo of planets exist out there in space. So continuing, we found another additional interesting system where there was an outer planet which was very heavy, like a gas giant, and there was an inner small planet around it. So initially, we just thought that's just a Jupiter and a normal paper would come out. But when we followed up, we saw that, oh, there are inner transits which are happening to the outer one. And this is also very interesting because if there is a Jupiter forming outside, it's very rare to form an inner planet. So that received quite a lot of coverage in the media because there are only a handful of such systems formed. So this was also very interesting. Now, coming back, I was mostly talking about solar-like stars, but I would like to point out to you that if you happen to look about what all are the stellar properties around which planets have been formed, this is stellar temperature versus the count, and this is surface gravity versus the count, you can initially see that most of the detected planets, they are around solar-like stars. They have temperatures which are like sun and also the surface gravity around sun. So what happens in this region? There is not much discovery space here, either towards the space which is subgiant kind of a population and also towards the space where the stars are like low mass stars or so. So this was realized long back, not by me, but by several other astronomers. And there have been now in the last decade several projects which are targeting to look at low mass stars, which were not really studied a lot. So at that time, long back, HARPS was one spectrograph which was churning out many Earth-like or Neptune-like planets. And it operated in a wavelength band, which is at the visible wavelength band, 380 to 680 nanometers. So it sat in the sweet spot where it could detect the peak emissions for solar-like stars. But if you want to study a star which is further red, which has its peak wavelength emitting somewhere around between 1 to 1.5 micron, building a spectrograph which has most of its visibility in the blue will not do good. You need a spectrograph which is more sensitive to that wavelength coverage. So I was lucky enough that I was involved with the Kamenis spectrograph when it started to take data, and I'm still a part of the consortium. And it's a great way to learn the near-infrared astronomy for me because I didn't do it while I was doing my PhD, but it's a fascinating world. There are more molecules, there are more complexities. And then we started the survey and we took a lot of data. So currently, Kamenis is actually one of the leading near-infrared spectrographs, which is contributing a lot towards the M-dwarf discovery space. So these are the cooler and lighter stars. And as you can see, all the stars having planets with the radial velocity methods are plotted in black. What you see in red and blue are the discoveries which have been contributed by Kamenis. You can easily see that you actually need special spectrographs to align to that particular wavelength range. So that intervention was definitely needed to bring out those pool of stars and happen the detection. Now this area is also populated by some other spectrographs which are also operational in that wavelength range. And Kamenis was one of the predecessors to start this. So it is really interesting. So if one wants to look at special kind of stars, one size does not fit all. So the same spectrograph would not definitely cover that range. So we have had interesting discoveries. We have found out how many small number of planets on an average would be present. So I think I wouldn't there is not enough time. I would just focus on few highlights. What we found out in our early papers and even the paper that we did last year, that there are nearly 1.3 small planets. Of course, the fraction is just it's not really a fraction, it could not be a fraction. But if you happen to find out how many planets per M dwarf could be there for periods up to 100 days, then they are nearly a little over one planet is present. So this is a graph which tells you in order of masses. So these are the smallest planets detected across the orbital periods, slightly intermediate mass planets, 10 to 100 Earth masses, and these are the giant ones. So the population of small planets is more common between 1 to 100 days. So it's also now kind of established that larger the stellar size you have, there's a higher probability of finding larger planets, which means gas giants are relatively more common around solar type stars. If you go to smaller kind of stars, which are K-type or M-type stars, then you happen to have more Earth-like or Neptune-like planets there. So this was something which was brought out by surveys like what we did. And then there were several interesting discoveries where we found out Earth-like planets, which means they were really tiny, had the same sizes and masses of Earth, and they happened to orbit very, very cold stars. Now, since these cold stars were absolutely inaccessible by spectrographs like HARPS, which couldn't go to those wavelength regimes, this was an area that we started to explore and had a great many discoveries. Also, we found out one thing, that the giant planets were not very common around M dwarfs. We had a couple of interesting discoveries. So one of them was that we found a gas giant which was orbiting one of the M dwarfs, and then we happened to discover another one across it. But these discoveries were not quite many. But if you see something which doesn't follow the norm, it is always more special, because probably more theories need to explain the planet formation mechanism. But then we also contributed, the survey also contributed quite a lot in the distribution of the statistical population of planets. So in small planets, which means planets which have a radius less than 4 Earth radius, they seem to have a bimodal distribution. So either there are planets which peak at around 1.2 Earth radius, and there is another bunch of planets which peak at around 2.5 Earth radius. So it has postulated that maybe there is something happening during the formation mechanism of the stars. All the planets could have had the same size, but the ones which are probably closer to their host stars, they actually lose their envelopes because of a lot of bombardment of flares or X-rays or XUV emission that happens. So this is an observational fact which was brought out by the California Kepler survey, which was done a decade back, and many people have agreed by doing several results. So with Carmenus also, we followed up several targets, and many of them which had more than one planet, we actually found out that the inner planet happened to have that smaller size, which means the envelope would have been actually stripped away, whereas the outer one happened to have the hydrogen-helium envelope given its size and density. So there were some interesting results that came out of this. But now the next part that I would like to highlight is, this is all about stars. When we talk about different stars, stars are not always quiet. When you detect larger planets, the signatures are very prominent, and it's easier to detect because the velocities are of the order of few meters or 100 meters per second. Now, just to bring to that perspective, this is a graph which was produced by Scott Goddy in one of the discussion meetings, where there was a discussion about how activity actually produces effects at the level of how it would affect the radial velocity measurements. So these are all the different things that stars do. And that's why we really want to talk more to our solar astronomer friends, because they give us the perspective of what actually the stars are doing. If we understand the sun to some extent, we can try to understand the other stars a little bit. So just look at some of the modes, like P modes or granulation that happens. It affects the radial velocities at the level of 1 meter per second. Supergranulation, that happens at this time scale of few days, and it also has the similar effect. Now look at 51 Pegasi b. The radial velocity semi-amplitude was 100 meters per second, oblivious to all of these measurements. But if you happen to have detecting planets at this range between 1 to 10 meters per second, then you are affected by granulation of the star, spots from the star, faculae, magnetic fields, so on and so forth. So it's not easy to detect planets in the presence of activity. So definitely there has to be interventions again. We do several things, but I would just perhaps highlight one or two simple examples, where what we do, we look at the signal of the stars. So whenever we collect radial velocity, it's always gathered over months or so, and we try to take this data to see if the signal actually sustains the evolution of time. If the signal happens to break in the strength, then you realize that there is an activity, which means that there could be a spot which is there on the disk. It leads to the radial velocity contribution, but then the spot vanishes over a few months. And if you build on the signal, it would not stay strong. For example, you just happen to look at the last part of the graph, where you see that the signal is gaining strength. It loses and again starts to gain strength. This is not definitely a planetary signal. A planetary signal should look like this, where it gains strength with every additional point, because every additional point would point out towards that planetary signal value. And as you grow with time, more observations you keep on stacking, the signal strength should just grow in time. So this is one example, the kind of things that we do to be sure of if the signal is planetary or it has some activity things in nature. But as I mentioned about, that there could be stars which could have like flares or so, they could be very active. So in order to account for this, we have like started a project where we are trying to look at very, very young stars and trying to look at these stars which could possibly have flare signatures and how these flares could actually affect any possible planets in that. So interestingly, I could just show you some early results. This is a very active star. Those who work a little bit on stars and flares, they would have heard about A. Leonis. Is a very famous M dwarf. It's a relatively young star, less than 300 million years. And it has roughly a frequency of 2 flares a day or so. So if you happen to look at just 3 different epochs, in the 2 epochs, you see that the star appears to have some nature. There is nothing much happening. But on one of the nights, as you can see, there is an enhancement towards the blue end, which actually indicates that possibly there is a flare capture. I mean, it's not completely, the data is not completely analyzed. We also have some more data, but I just wanted to point out that this exercise is done to understand how the flare would actually, in principle, affect any possible planet which could be present. And these are interesting avenues where one can look at, especially young stars, to make this more relevant. So I think in summary, I would like to say that the discovery of wide variety of planets around different kind of stars is really important, because that makes us understand the whole architecture of exoplanetary systems. And it's not only just understanding or making your telescopes better, it's also understanding the host stars and applying special algorithms like disentangling the stellar activity or making certain different interventions in order to make that corrections to enable the detection of smallest of planets around some difficult stars which could be really active. So that plays a very major role. So before I end, I think since this is a gender equity workshop, I would just want to, in 2 or 3 minutes, want to say that it was, I mean, it's a great pleasure for me to be here, and it's very nice to meet all of you and discuss your all stories. I would like to mention that when I started my PhD, I was not, I mean, I would say I come from a privileged background, because I was not allowed to do PhD or so. But they were my family was very agnostic about my research. Neither there was a support, nor there was a no to anything. You do what you want. I think that was a very much like a blessing in disguise, because nobody questioned or wanted to know. If I said I can't do my PhD, I want to quit and go back, I think they wouldn't have cared. But they were always, okay, finish it. If you like, you finish it. Perhaps after I got a job in TIFR, they perhaps now appreciate a little bit, oh, finally you are earning for what you always said that you're studying. So sometimes there are things which not are always look rosy to somebody, but keep going on is the only picture. There had been several days in my PhD life where I found, probably this was the case even when I did my postdoc. Oh, I am probably not good enough. I should leave it and go back. And then when I looked at my results, I found like, okay, that there is still hope that I should keep continuing. So I mean, the consistency is the only thing that keeps you going. And I think most of us suffer from imposter syndrome, but I think there's a good chance that we should hear ourselves and maybe another person saying, no, you're not bad, it's all going good. That kind of helps. So thank you for all the mentors who have done this to me. I really mean that. They have influenced me, be they men or women. Thank you for that. And also to my fellow colleagues who are here. It feels very great to be back and have a nice group here. Thank you.
questions.
Very nice talk, Priyanka. So I am not from this area, so I have a very naive question. So I understand that this Jupiter or this massive planets, they form away from the star and then somehow they move in. So why, like how, and then you also showed this histogram where you see that most of these stars are around sun-like stars. So why it hasn't happened in our solar system and why is it happening in systems where you are detecting hot Jupiters, Neptune like planets?
That's a very good question because for some time it was hard to believe that such things could be there. I just think that our solar system is very unique in that sense, but we have several examples where there have been stars and planets very close to it. One common theory that has been, like, there are 2-3 mechanisms. There could be migration or there could be a third body in the system which actually leads to this eccentric tidal migration to it. But then there are certain things which breaks the law. In situ formation is a very difficult thing to explain because it's hard to say that there is enough material that close to the star that it can form a planet. So most likely migration is something which is tried to answer this question. That's why it's imperative to look at the atmospheres of such planets, because if you look at the carbon to oxygen ratio through the atmospheres, then one can say if the planet would have formed below, earlier than the snow line or further away from the snow line. And that can give you some insights. Not everything is solvable, but we just speculate. I would just say that solar system is very unique, that we don't have such a system. Maybe it was how planets formed in our solar system early on, and there was Jupiter formed pretty early. It had a lot of mass accreted and just stayed there. And there were other planets also which formed. So yeah, that could be one thing.
Thank
yeah.
you.
Thank you for a nice talk. I think a follow-up question for this. You showed one of the results in which M dwarf has not M dwarf, a sun-like star has a Jupiter, as well as a smaller planet that had inside the,
Yeah.
I mean, in between these two.
Yeah.
Also, you mentioned that this is a very rare case.
Yeah.
So also we see a similar kind of system in our solar system. So what could be the reason for that?
So this and our solar system are slightly different. So what I meant why this is rare, because this is a hot Jupiter. The first outer planet has a period of around 4.4 days. So it is orbiting very close to its star. Normally in situ formation or forming right at that place is not expected for such a system. You would expect that the planet would have formed further away, and while these planets migrate, they actually migrate everything inside it. So you wouldn't expect a smaller planet to be there still. It should, if it would have existed, it should have merged already, either fallen into the star or it would be part of the hot Jupiter. So existence of such small planets makes it very tricky. Maybe that the migration was so slow that the small planets survived. And there are a couple of examples. I'm not saying this is the only one system, but they, like, such discoveries make us think what could be different in such systems. Maybe the migration was slow, or maybe there was in situ formation along with, and there wasn't enough time for these two planets to merge together. Maybe in some time it falls, but we do not have those time scales of observations.
Thank you.
Ma'am, can the stellar activities be used to detect planets?
Stellar activity actually affect the detection of planets. So when they are present in the data, they work like nuisance to planetary astronomers because they need to take it out. But having said that, I mean, both of these things coexist. It is not said, like, it's harder to detect planets with around active stars, but there are planets even around active stars who might have not been detected just because of the activity.
But can that activity be used to detect planets?
Can that activity be used to detect planets? That is a very difficult question to answer because I have to think about what you're seeing. Directly, I don't think it can be used to detect planets. Yeah.
And I have one last.
We can discuss if you have a follow-up thing, because probably I did not could understand your question very well. Yeah.
Yeah, I think you can chat over coffee.
I would like to check quickly if online there is anyone who would like to ask a question. We can take one. Please unmute and ask the question online, participants, if any of you have.